Today we're moving on with our kind of general discussion of functions. We're going to talk today about symmetry. And there's three kind of major types of symmetry that we're going to talk about in this course. So the first kind is symmetry with respect to the x-axis. With respect to is a common mathematical phrase. I abbreviate it with WRT. You're free to write it out or use the abbreviation. Either is fine. So when we talk about symmetry, at least to get a handle on kind of what's going on, a picture is often really kind of helpful for us. So this function here that I've written is symmetric about the x-axis. Because if I take one side of the x-axis and reflect it, it would lie exactly on the other half of the graph. So if I reflect the one half across the x-axis, I would get exactly the other half of my graph. Everybody's okay with that? It's basically mirror image, right? Where the x-axis is my mirror. Okay. Just as a quick observation here, notice that something that's symmetric about the x-axis can never be a function. Everybody observe that? That if you have a mirror reflection across the x-axis, you're automatically going to fail a vertical line test. The general term, again, that we use for something that is not a function is a relation, just as a review of that vocabulary. So this guy, our example prior, was a relation. So we have symmetric to the x-axis. Not surprisingly, next we'll have symmetric to the y-axis. So again, same idea, except this time our mirror is not the x-axis, rather it's the y-axis. And the last kind of symmetry that we'll talk about is 180-degree point symmetry with respect to the origin. That's a mouthful. What that'll look like, though, is something like y equals x cubed. So what this is saying is, if I take like the part of my graph from the origin and I rotate that 180 degrees, it would lie on the other half of the graph. Everybody's okay with that? Alternatively, you can think about it as a reflection across the x followed immediately by a reflection across the y, or vice versa. So for example, if I reflected this across the y, and then reflected it across the x. It's the same thing as doing that 180-degree rotation. Everybody remember kind of these transformation terms from geometry? I know that was a long time ago. We talked about reflections and rotations and such. So if I look at the graph, I can use my eyes to kind of determine if something is, which kind of symmetry we have, right? What if it's just really close? Well, what if it's like it's, you know, like if you're doing it just visually, can you tell if it's exactly a reflection or just really, really close to a reflection? You probably can't tell exactly, correct? So just to kind of illustrate what I mean, let's say I have y equals x squared from 0 to 10. So that's going to look like this, right? And what if I do y equals x squared, 0.99 times x squared from negative 10 to 0? If we look at these, do they look like they are symmetric about the y-axis? Absolutely, right? If I actually reflect this one over to the other side, it's even so close that I can't tell the difference when I do have it graph and do the reflection. If I zoom in, you're starting to see that there is a little bit of a gap between those two. And the more I zoom, I gotta move this over. Move over. You can see that they are not actually lying on top of each other, right? You see that there's distinctly two separate lines here. So in that sort of situation, it's not really very realistic to tell if it's actually symmetric about the y-axis or not. At first glance, we probably all would have said yes, right? So what we want is a non-graphical method for doing this, or for being able to check for these kinds of symmetries. Ideally, what we want is an algebraic method, and we actually have that. Come on. There we go. So if I go back to the reflection across the x, algebraically, that would mean that f of x equals negative f of x. So I could use that to check to see if I actually have that kind of symmetry. We have a special name if something is symmetric with respect to the y-axis. We call that an even function. And algebraically, f of negative x should equal f of x. And for the third type, we have a special name for this. We call it an odd function. And algebraically, we have f of negative x equals negative f of x. That's our check there. So let's do some examples of how we can use these rules here. So my direction here says that prove that each function is odd, even, or neither. So the first one we'll look at is f of x equals x to the fourth plus 1. What I would do first is I would start by graphing x to the fourth plus 1 and looking at the picture to give me an intuition about whether I should be trying to prove this to be odd, even, or neither, because it's usually pretty hard to prove something is odd if it's not actually odd, right? So if I look at this, this looks like we are symmetric about the y-axis, which means I'd be trying to prove that it's even. Everybody agree with that from looking at the picture? So we're going to claim that f of x is even. To prove that, we want to show that f of negative x equals f of x. So WTS is, again, a common mathematics abbreviation. It's a phrase we use a lot, which just stands for want to show. So oftentimes inside of a proof, like I state what I'm trying to prove, in this case that f of x is even, and then in order to show that, I state what it is that I need to do in order to show that. Okay. So if I want to do f of negative x, all I really need to do is plug negative x into x as if I was just evaluating a function. So that's going to give me negative x to the fourth plus 1. Now if I simplify, negative x to the fourth is the same as x to the fourth, because I know that if I multiply 4 negatives together, I should get a positive. And this is exactly f of x. Everybody see that? So we're done. So I draw that little square at the end to indicate that I finished my proof. But notice what we did here. We started with f of negative x, and we showed that's equal to f of x, which is what we needed to do in order to prove that this thing was even. Everybody happy with that? Okay, let's do some more examples. I know when I start using the P word like that, people get all bent out of shape, but these proofs are not terribly difficult. So what about g of x equals 2x to the third plus 3x? Just like before, I'm going to start by graphing this and looking at the picture to give me some intuition about whether I think I'm looking at something that's odd, even, or neither. Looks odd to me as well. Let's try to prove that then. So to show something is odd, I need to show f of negative x equals negative f of x. So I'll start the same way. I'll plug negative x in place of my x's. And then I'll simplify. So 2 times negative x to the third just becomes negative 2x to the third. And 3 times negative x just becomes negative 3x. And I notice that each of the terms here is negative, so I can factor a negative off. And 2x to the third plus 3x is the same thing as my f of x. So what I've shown then is f of negative x equals negative f of x. Quick question as an aside at this step here. Why didn't I factor out a negative x? Right? There's an x in common with each of those terms. Why wouldn't I have taken a negative x out? What am I trying to get to at the end? Negative f of x, right? So all I would ever want to factor out would be the negative part, because we want the f of x left alone at the end. Everybody happy with that? Let's do one more. Now, by the fundamental rule of mathematics examples, what kind of function do you think this one's going to be? Odd, even, or neither? Neither, right? We've seen an example of even. We've seen an example of odds. If there's 3 things and you're giving me 3 examples, I'm betting the last one is the whatever's left over. Usually a safe guess. But let's look at the graph and just kind of see what that looks like anyways. It is a quadratic function, and some of the quadratics are even, but not all of them are. Let's look at this one and just get a good idea of why it's not even. Ooh, excuse me. Well, this was just a... That's fine. So let's just do that. Oops. Gosh, dang it. Dagnabbit. So if I look at that, notice that that's not exactly symmetric about the y-axis. The right-hand side looks to have slightly more of the graph on it than the right and then the left-hand side does. Everybody agree with that? It's subtle, but it should also be obvious enough that you should notice that. Everybody agree? So we say that this is neither. So we need to show actually 2 things. We need to show f of x is not equal, or I'm sorry, negative f of x is not equal to f of x. F of negative x is not equal to negative f of x. So basically we're just going to show that it's not even and not odd. Everything else is the neither category, right? So I'm going to start the same way. So I'll do negative f of x. And when I simplify this, I get 4x squared plus 3x plus 9. Everybody agree with that? Well, that's definitely not f of x. What's the difference between this and f of x? Yeah. Everybody agree with that? Okay. If I factor out a negative, I also notice that this is not negative f of x, is it? So I'm done. I've shown that it wasn't f of x, and I've shown it wasn't f of negative x. Questions about odd, even, either? Okay, felt fairly straightforward, I hope. The checks are pretty easy. On to the next topic. Which is about asymptotes. If we were to give a definition for what an asymptote is, what would we say? Okay. Val? Good. So we combine those two. I think it kind of covers it. So the approaches, but never touches, or crosses, I think is what we're looking for there. Because it has to be one of those where the graph is getting very close to it. Like I can't just say something's an asymptote just because it doesn't cross it. So if I have a parabola, like those aren't horizontal asymptotes because the graph never crosses them because it doesn't approach them either. So you need both approaches and not crossing or touching. But that's good. We say an asymptote of a graph is a line that the graph approaches but never touches. And again, if you take calculus, or when you take calculus, you'll get a bit more rigorous definition of what an asymptote is, because what the heck does the word approach mean? Well, actually, you'd formally define what that kind of means in a calculus class. But it basically means I can find a value for x that the function can get where the distance between the function and the asymptote is as small as I'd like it to be. And in fact, as that distance between them decreases, we get closer and closer to some specific value. All right. So, when we talked about asymptotes last year in Algebra 3-4, how many different kinds of asymptotes did we talk about? 3. Okay, so you had vertical for sure. What else? And lastly, slant or oblique. We're not going to worry about these right now. And when we talked about rational functions, did we always have a horizontal asymptote, or did we sometimes have something that was close but not exactly? We had some stuff that was often close but not exactly. So, for example, let's say we are looking at this graph, and I'll write down the function for that corresponds to this graph here in a moment. Just kind of a lot of drawing for me. I'm no art student, You know, guys? Well, it's why I chose to get good at math, because I certainly wasn't any good at art. Not that you couldn't be good at both, you know. There's a lot of people that are good at math and also good at, like, music, like performing art. But when it came to things that required, like, a good amount of dexterity, I was not usually quickly good at those things. As you might have guessed looking at my penmanship, that probably isn't much of a surprise. Could be worse. You've probably seen worse penmanship. But, I mean, I try to be reasonably clear. I'm actually getting better at writing on the tablet than I was when I started. It's a different experience. You guys have tried. It is kind of hard. I think it's worse when you're left-handed also. Like that, I think, makes it really hard to write on the tablet. As you're, like, trying to go do this, reaching across your body, I think just makes it a little bit harder. And then you're, like, dragging your palm potentially across everything you just wrote. Anyways. So notice here, the function that I've drawn, does this have a horizontal asymptote by the strict definition? Michael, you say no. Why not? Yeah, so he's saying we have a crossing right here. Everybody notice that? In Algebra 3-4, what did we call this situation? We would call that an end behavior rather than an asymptote, than a horizontal asymptote. Do you vaguely recall this? Well, it's okay if you don't really, because as far as we're concerned for right now, we're just going to call that stuff a horizontal asymptote, whether it's an end behavior or not. So I'm still going to count that as a horizontal asymptote. If you call it an end behavior, I wouldn't mark it wrong. If you call it a horizontal asymptote, I'm not going to mark it wrong. I'm going to let you use those two terms interchangeably right now. I'll let you know when that changes, but for right now, I think that's fine. Is that okay with everybody? C? Do you guys remember how to find vertical asymptotes from last year? At least in a rational function. Let's limit this to those situations. So a rational function doesn't have a square root. It's going to be similar to the example I gave here. Okay, so a lot of what you're discussing, I think you're talking about horizontal asymptotes. When you start talking about degrees of numerators and denominators and such, that's a horizontal asymptote thing. So, Val, you said, what did you want to do? Yeah. So the first thing you'd want to do is try to factor and reduce. So if I look at the numerator, can I factor x squared plus 3x minus 3? Oh, we need to make a decision. You said both. Can we factor x squared plus 3x minus 3? No, you cannot. There aren't two numbers that multiply to give you negative 3 and also add to give you positive 3. So there's nothing to do in the numerator. Can we factor the denominator? Okay, what does the denominator factor to? Multiplies to give you -3, adds to give you +2, right? Hopefully, after a brief refresher on that, you'll remember how to factor again. That is an expectation for this course, is that you can do that kind of simple factoring. JJ, you happy? Okay, you're just making some faces. I just want to check. Okay, so Val said to factor, which is what we did. Then what do we need to do? What is them? Good. So then we would, if there's any reducing, we would want to do our reducing. Since the numerator cannot factor, there's no reducing to worry about. So then we would just set denominator equal to 0 and solve. And since they're being multiplied, setting the denominator equal to 0 is equivalent to setting each factor equal to 0. So we get vertical asymptotes at -3 and +1. And if you went back to the graph that we sketched above, you would notice that that matches. Okay? So not too terribly difficult to do. The one thing you need to make sure you remember is make sure you reduce before you set things equal to 0 and solve. Because if you cross something out of the denominator, that doesn't generate a vertical asymptote. Right? What happens for what do those generate? Does anyone remember? When you cross something completely out of the denominator? Yeah, that creates the removable discontinuity, a hole in the graph is what that did. Again, not an expectation that you remember all of this rational function stuff in super detail. Knowing how to find a vertical asymptote, though, is something I would expect that you still can do. Which is not too bad, right? It basically boils down to being able to factor and solve a polynomial, which is typically not so bad. And I'm going to put a little asterisk with the horizontal asymptote just to say that we're including those end behavior things like we detailed in that first graph that we drew. So that's all that asterisk is referring to, is that we're also going to include in here situations like in the graph where we have almost an asymptote, but it might have like one little cross in the middle, but the end behaviors are asymptotic. I know that's a fun word to say. All right. Does anyone remember how to do this? Yeah, so there's 3 situations where we have degree of the numerator greater than the degree of the denominator. We have less than, and then we have equal to. Okay. In the situation that the degree of the numerator is greater than the degree of the denominator, that's where we get the slant asymptote. Do we have to worry about that for right now? Nope. If it's less than, we're going to have the same thing for any situation where the degree of the numerator is less than the degree of the denominator. You'll have an asymptote or end behavior at y equals 0. And if they're equal, our asymptote or end behavior will be leading coefficient of the numerator over leading coefficient of the denominator. That's supposed to be, yeah. I wish you would have. Wouldn't have sat up there for as long if you just said that there's a mistake there. Okay. So if we go back and we look at this first example, what's the degree in the numerator here? It's 2, right? Because the biggest exponent is an x squared. How about the denominator? That's degree 2. So the degrees are the same. So to find our horizontal asymptote, it's going to be leading coefficient of the numerator over leading coefficient of the denominator, or just y equals 1. Everybody okay there? Now, do you need to have those rules memorized?
No.
Yeah, we can kind of determine this also with our calculator. So let's do that and just kind of show you how that looks. So I'm going to type in this equation into my calculator. I'm going to type it in as a fraction because I typically think that's easier to do. To access the fractions option on your calculator, the fastest way to do that is press alpha and y equals. The one I want is just numerator over denominator. And then I can type this in exactly as it looks on my sheet of paper, which is nice because I don't have to monkey around with a bunch of parentheses or anything. If you press the alpha button and then the y equals button, that'll open the fractions menu for most of you guys. As long as you have a calculator that has the rechargeable option, I think that's the same time they changed their operating system and added that shortcut. So as long as you have a rechargeable calculator, I think that works. And even some of the newer battery-powered ones, I think still have that shortcut. It's been a while since people haven't had that. But unless you have like an old calculator, you probably have that option, or that shortcut. So if I hit graph, so here's my function. So it looks like we have some asymptote behavior going on here. To confirm that, if I go to my table set, and maybe I start at negative 1,000, and I look at the y coordinates in my table, looks real close to 1, doesn't it? If I do the same thing and change my table set to maybe start at positive 1,000 and look at my table, real close to 1, right? But not actually getting there. At this point, I'm pretty convinced that the asymptote there is at positive 1.